Hello everyone. Welcome all on Data Phoenix webinar. Today with us Mark from Gradient. He is co-founder and chief architect, and we will speak about training an expert financial LLM. Previous I give him microphone, I want to introduce you to our new website on which you can see our streaming today. We launch it as the calendar of our events and as well interesting events globally. So if you organize some event, you can add your event to our calendar and we will happy to promote it through our channels as well. Also, what we want to test today on our webinar, it's options when you can join our studio and ask live your questions and have discussion with Mark. So if you want to join in QA session, please write in the chat that you have the question and want to join, and I will invite you to our studio. Also, you can ask your question in Slando, and we will try to answer to all the questions. But if the time is over, we will continue answer in our Discord. So I give the microphone to Mark, and we will start.
Hi, thanks for having me on board at Data Phoenix. You've been doing some great things. I definitely think that anyone who has an interest in sharing your knowledge to the community should hit up Dimitro. He's running a great program over here. But in terms of sort of introducing myself, I'll start with my presentation first and give people a look into what we do at Gradient. So at Gradient, we are in the business of AI automation for enterprise use cases. In particular, we focus on using agents to perform automation tasks. And we operate in the financial services industry. So there's a lot of nuance that has to be incorporated in from the model upwards. So I'll talk a little bit more about how we trade an expert finance LLM. And in our case, we called it Albatross, and we've open sourced an early checkpoint of it where the community can adopt the model and test it out for their use cases. So to start, I wanted to talk about and lay the foundation for how foundational models are growing and they're being released at record pace. But there's a little bit of a gap in terms of the core components of things that they can be used for and why we actually need more specialization for some of these models for enterprise use cases. They've been making a lot of strides in various sectors, but immediate examples for finance today that we see are for the text mining, sentiment, or quantifiable signals extraction use cases, taking in unstructured data to inform investment decisions, such as customer service, and internalizing the interface for internal knowledge. More recently, we've actually seen emergent use cases that are like more personalized investment advice, suggesting positions for an investment's individual constraints in historical trades, and analyst assistance. But the value of these applications are definitely growing. So at Gradient, we work with a number of institutions, like I said, to deploy their LLMs into their operational workflows. And large banks have actually been starting to publicize their adoptions. For instance, Morgan Stanley themselves have embraced OpenAI and have used it as an assistant for financial advisors. Another good data point is Goldman Sachs using their LLM to monitor financial news and social media for potential risks to investments that are actually more orthogonal to the traditional time series use cases. Now, why did we actually go about building Albatross at Gradient? Even though the commercially available large language models were great for prototyping and they had their general capabilities, they're still blockers for embedding them in production financial applications. So, like a Swiss Army knife, Generalist LLMs are unwieldy and more involved in demanding use cases, especially without an experienced hand to guide it. So you'll find for financial applications, generalists, they usually underperform on industry specific tasks and are a little bit more costly, or actually significantly more costly to run than the smaller models. Um, I'll go into three of the main reasons why direct application of even the most specific, most sophisticated generalist LLMs are not likely to succeed. It's really comes down to the lack of domain expertise, um, because there's a recent JP Morgan paper, probably in the last 6 months or so, that showed GPT-4 underperforming for structured NLP tasks. These include things like NER or relation extraction. So if you really think about it, these classical models and some of the more domain specific models are actually trained on the finance domain data, and that allows them to have more nuanced extraction capabilities. In addition to that, they're not really built for uh, specific use cases. So generalist models don't really involve thinking about the nuanced subjective uh, questions or following user instructions for these use cases. So you'll really notice, because they're large and they're really trying to work on the distribution of any possible person who'd be using them, there's positional bias as well as other types of specific distributional bias that have happened in the pre-training of these models. So they're not really targeting that specific performance. Finally, productionizing them requires really deep customization. So like if you want really high accuracy for some tasks, you're going to have to customize it and reduce the rigorous hallucination levels that you need in terms of like rigorously tracking and auditing the accuracy and the bias to require access to the model's inner workings. So I want to introduce, what we did at Gradient when we built Albatross. So this is a specialist model rather than a Swiss Army knife, like I was mentioning before. So there's been a bit of related work that's been done in this space that I'll go to in a second. Before that, I'll go over the training pipeline overview for the main stages that are involved in training these models. We didn't pre-train from scratch, so I'll differentiate our technique from someone like Meta, who took 5 trillion tokens and pre-trained their model from the very start and then put it through their entire training pipeline. What we view ourselves as specialists on is the post-training process. So by that we mean we took an unlabeled corpus, and that's a continual pre-training step that you can see in this first stage. And then we synthetically constructed labeled pairs that targeted a breadth of tasks that would be useful for the downstream applications that we're actually going to be using. And then finally, we applied preference optimization that took pairwise comparisons of different responses from the model to see like which ones were to align the model more for what is the preferred generation. So that is always, or not always, but typically the case for any sort of chat-based model. And we apply that in order to provide more robust capabilities and usage patterns of the model downstream for applications. Otherwise, you'll notice that if you only do supervised fine tuning, the model can only answer questions if you use a very specific format to prompt it. Now, I wanted to start off with understanding what the requirements for financial applications are, because without those, you really don't understand how you can focus and customize a model in a way that will satisfy the user and also be enterprise grade. Um, it really comes down to six high level components, and we're going to focus on domain knowledge, consistency, and hallucination, as well as tabular understanding, because the other set of requirements like reasoning, audibility, and efficiency, they come as table stakes within the model itself, and it's more of a process of either supporting the inference of it, or also being able to have some observability. And with respect to the reasoning, you're really pushing the boundaries of the LLM capacity for logical reasoning, which it's more about eliciting the right response from the base pre-trained model there. So I'll first start off with talking a little bit on the domain knowledge aspect of things. There's already been open research on how some people have been incorporating data sets into their models and customizing them in the post-training process. On the right side, this is a visual. And what I want you guys to take away from it is the fact that, as you can see, the top curve there has the highest accuracy, but it's also one of the smaller models. Whereas on the bottom, you see the gray or the other larger models starting to underperform as you increase the number of relevant pre-training documents. So why is that? Well, the reason for that is the fact that general purpose LLMs like GPT-4, they might be a little bit more deficient in specific financial subjects because of their broad training data. And what happens are the fact that language models, they'll perform poorly when answering questions on rare knowledge in their training data set. So this figure um, reproduce some of the aspects of incorporating trivia QA questions as a part of the relevant documents that they're going to be trained into the model's pre-training data. So in this visual, the researchers evaluated the blue model and found what relevant documents were in the pre-training data, and then took non-relevant documents and tried to see the accuracy of that. So it really shows that rare tokens are hard for the model to handle. Now, in incorporating that data, the next step is understanding how do we actually find specific rare tokens that aren't in the pre-training data, and how are we going to curate and incorporate them into the model itself. So um, it follows three main steps, as you can see, and I'll talk more about each individual one. So on the membership inference side, what we're trying to do is we're trying to knowledge probe the model and use statistical techniques to find where tokens that don't already or are unlikely to exist in the pre-training uh, are. So you take a set of data or a corpus that is outside of the model, and then you try to compare and probe the model to make sure that those tokens aren't already been trained into the weights. So what we did is we took a likely ratio attack. So that's Lyra shown over here. And what that does is it compares the empirical distribution of the perplexity of samples from a candidate data set to data sets known to be in the training data. Now, afterwards, what you do is you actually take a hypothesis test using the Kolmogorov-Smirnov statistic to figure out and give an automated first pass for seeing what the domain curation can be, and allowing for substantially more capacity to crawl for relevant raw data. So this kind of reduces the need for human involvement and helped us scale out our data collection process. Um, and the second set of steps, we actually use human evaluators. So we had actual financial professionals from a broad range of different finance functions to review the set of data that we wanted to incorporate into the model, so that we further filtered it to the more high quality data sets within the financial domain. So that also involves rigorous cleaning and pre-training to pre-processing to ensure data quality and consistency, as well as standardizing formats to ensure that the data aligned with the expectations of what we'd be seeing in the financial downstream tasks. Now, as a final step, we actually had to take all that data and we produced even more data. So that is the synthetic data generation process. So we used it in order to get more tokens out of it broadly, but also, which is the most important step probably, it's to better represent undersampled data. So we want to train the model to better cope with the variation in data representation and formatting. So we kind of have, a paper out there where you can see the table of our reflected corpus. So I'll give a little summary of what happened at the very end and what our pre-training data sets look like. So the first the core of our pre-training data sets are what we call the finance text data set in the corpus. These are a proprietary set of mine text financial texts from SEC filings and public articles. And then we actually use embeddings on this on the corpus below to retrieve some finance specific terms out of the red pajama data set. So we actually went through the 30 trillion token open web crawl data set that's available, which has a lot of low quality tokens in there too as well, to filter out and grab the ones that were relevant for finance. And finally, we did the same thing, but for code. And the reason we did that for code is it's been shown that with code, there is a strong correlation with reasoning, and we want to bump up the reasoning capability for financial specific reasoning capabilities within the model. So the next aspect of things that really came to fruition after we've collected the data is thinking about the consistency and the hallucinations that could occur. So what really happens in hallucination is that the model, when it cannot act, when it has lower probability responses or tokens being generated, and it cannot answer the question, it doesn't know the boundaries of which its knowledge exists. So by that I mean it's more likely to be providing a made up or untrue statement because it's unable to answer the question. Whereas if you have viewed and seen a few more powerful models such as GPT-4, it's really well adept at knowing, hey, where its knowledge cutoff is. So what we had to do after we've trained this new corpus in there is to ensure that these tokens are elicited in the correct fashion, and the model also knows the boundary at which its knowledge capabilities exist. Generating ungrounded content is probably the biggest hindrance to deploying an LLM into a critical environment. So, um, comprehensive hallucination mitigation would include a lot of suites of systems or retrieval augmented generation or knowledge graph or even truthfulness probing. Um, in doing that, though, what we really needed to do is we had to curate a lot of our data and look at the inherent biases and the distributional biases to anchor the model in a more consistent knowledge acquisition. So we fine tuned it on a range of data sets that are selected to improve relevant generative ability. And these include document summarization, open book training, and name entity recognition. Um, that's sort of the visual I'm going to provide here, and I'll jump into it a little bit more. The fact that document summarization reinforces the importance of the information gathering capabilities of models. So it's a distillation of concepts in a widespread and diffuse set of tokens. So grabbing really large pieces of context and be able to get the linkages of that information. And that's becoming more and more powerful with long context models. Um, Additionally, we have the open book training aspect of things like self-RAG and open book QA. Those are useful for the consistency and alignment with existing information. So that actually taught the model to cross-verify outputs against a knowledge base, forcing a grounding mechanism in its generation process. So we train that into the weights of the model, basically. Finally, again, as I had previously talked about in the JP Morgan research paper, extraction tasks tend to be hard on domain specific tasks for generalist models. So we also wanted name entity recognition to train into the model more in the corpus to act as a safeguard against hallucination and anchor the model more on recognized entities in the financial domain. These could be things like, what do certain acronyms and certain phrases, what do they actually mean in practice, and how the model can recognize those and ground itself. Um, the final step that happened within the training of the model was the preference optimization. Here, I wanted to go over the set of in corpus that we used for this final training phase. And in this stage, we curated a combination of a lot of open source and some proprietary data sets. So I'll just point out a few of the ones that were incorporate proprietary data sets inside of them as well. The alignment data was synthetically generated on our part. We used GOAT data set from Hugging Face to bootstrap our math data set. And also the tabular data set, as we said, played an important role because we were targeting tabular understanding. Now, this corpus comes um, in order of the size of tokens that were in this total corpus. So these categories, the highest is chat for a specific reason, and that is because the alignment layer and the preference optimization layer is integral to having the model steered correctly. And without that, after you continually pre-train, you run the risk of underlying the model. That's one thing. And that should be considered orthogonal to catastrophic forgetting. So in the case of catastrophic forgetting, what's really happening is the model just unlearns or forgets a lot of the downstream capabilities it has. This should be different from becoming unaligned, in which case the model still has those capabilities, but they're inflexibly elicited through uh, specific formats. So always having to have a instruction format passed to the model and making it difficult for it to chain together multi-prompt reasoning steps. So that's why we added more chat and alignment tokens in this final preference optimization, and then also added some sense of being able to produce well steered generations from tabular data and math and some of the open book data sets too. Now, I think I should dive in a little bit more into the tabular understanding aspects of the model since they were so important in the construction of it. For tabular understanding, it's really important for the model to be able to manipulate data in an industry that basically runs on numbers, right? Like the finance industry is centered around numerical analysis and leveraging semantic context and knowledge to apply those reasonings on tables. So to be able to extract this information, models have to comprehend their tabular structure and perform that reasoning easily. Uh, a simple example would be like considering investment decisions that depend on projected or discounted cash flows pulled from a company 10K annual report. That requires finding and filtering a relevant table, forecasting a trend from the data, and appropriately discounting and aggregating forecasted values to finally suggest an investment decision. So a financial analyst, they'd use a combination of prior knowledge in how SEC tables are structured, as well as formulas and spreadsheets to arrive at an answer. So this intrinsic knowledge to interpret and manipulate a cash flow table and the ability to perform calculations, that those are all important, and neither are sufficient on their own. So in our internal testing, here we found that generalist models are unable to perform tasks at equal or lower difficulty uh, uh, to these aspects. So we're comparing the performance in the table for the commercially available models like GPT 3.5 and 4, and then Mistral Instruct on table summarization task that we created. So the task asks the model to extract and summarize information from a financial table, computing sums and percentages. And these were the overall task accuracies, which they're okay maybe on GPT-4, but they're certainly not passable in the open models or even the non top frontier models like GPT 3.5 when we were doing these benchmarks. So for Albatross, we want to accomplish and make this better, right? We want to give it sufficient training data to learn the tabular structure and perform numerical reasoning. And our key insight is that a single table structure is brittle. So we had to do manipulation of the formatting of the tables so that the model could use positional context and figure out how to index different numbers in the tables properly. I'll dive into a specific use case that we use our model for, and that is for financial investment analysis. Suppose in this case, like you want an investment decision that depends on discounted cash flows, and you're pulling that out of 10K. So, as I sort of talked about before, you do this by surfacing all the different information across tables and text to come up with that. Now, the main outcome that we were able to support out of that was that we found the difficulty in the models being able to accomplish this, and we wanted to build the model ourselves from the ground up. And that sort of led us, in all these learnings on a concrete use case to need to build Albatross. Now, what we did on tabular understanding is we started off on the supervised fine tuning step, and we gave the model sufficient training data. And these included some of the aspects of function, our finance functions. So the gradient finance functions are just a specific and specially curated set of financial equations and data manipulations. So these are commonly used manipulations and transformations that people in the financial sector use to generate the proper inferences from the data they collect. Now, we provided the model expertise in that specialized function calling in addition to that, because if you think about how typical agents perform today, right? This is really the year of having autonomous automation. They leverage tools, and these tools are nothing more than figuring out what API specs are and then generating code that can be executed by Python or some sort of program runtime to better improve their capabilities for these tasks that they weren't trained specifically to do. And then finally, this leads to better tabular understanding because the model can now extract, understand, and manipulate the tabular data much better. So I'll sort of close out this talk and show you what the results of all of our hard work led to. At the time when we created the model, the top open source models available were Llama 2 and Mixtral. We trained our model and then evaluated on three main benchmarks. So we focused on the GSM-8K, which is a proxy for mathematics, and H6 is the Hugging Face Open LLM leaderboard, and that is a composition or an average of MMLU, Trivia QA, and a bunch of other standard evaluations that test a model's total knowledge capability as well as language understanding capabilities. And then finally, in the yellow, we constructed a proprietary data set using SEC tables that focused on tabular reasoning, so taking aggregations on top of tables or taking sums or finding the location of multiple values within SEC tables. As you'll see in comparing all the models, we're able to push the performance of an open source model, which we use the base model Llama 278B, above and beyond all the other open source models at the time, and even rivaling and exceeding GPT-3.5. And part of that was, in summary, a very well curated synthetic data generation process, focusing on the key components of what was necessary in the downstream use cases, and then creating a training pipeline that was able to allow the model to flexibly accomplish the tasks and align it for what a user would be using it for in their specific finance domain use case. That's all for my presentation for now. I guess we can probably open it up for Q&A at this point, and yeah, I'll let Demetrio manage that.
Yeah, we have a lot of questions, and I want to repeat that if you want to join Studio and ask live your question, please write in the chat and I invite you. And I will share Slando where we collect a link. One moment. So yeah, first question about how much it costs to create fundamental model, and would it be worth to do this exercise for other domain like healthcare?
Good question, and we actually have we've actually done it for healthcare. It's not the exact same process, but uh, again, what I'll sort of differentiate is the fact that we did create, in a sense, a foundational model, but we focused on the post training, so it wasn't as expensive as Meta having to spend tens of millions of dollars training the model from scratch. So we were able to do it within the confines of, you know, an early stage startup trying to accomplish that.
Good. Can you share why you chose DPO versus Perf or LoRa uh, LoRa
Yeah,
technique for fine tuning?
those are all. So, yeah, I'll differentiate a little bit. Like DPO is preference optimization, and that will we use that in combination with full fine tuning. Now, the reason we didn't use LoRa fine tuning is that using when you have low rank uh, fine tuning, the gradient propagation back to make the model learn completely new tokens and new abilities is less impactful than if you use full fine tuning because you're propagating all of the gradients back through the entire network. And lower base fine tuning has been shown to be really useful for very specific tasks, but not as generally useful when you want to have a composition of tasks.
Good. Mark, did you benchmark your approach against RAG? Uh, Also, why RAG was not preferred here?
Yeah, I think it's a good question. There's always there's always a question between like fine tuning and RAG. In particular, for our use case, RAG wasn't sufficient because what RAG does is it either updates the knowledge of the model or it grounds the model. Now, what we needed were more fine grained reasoning capabilities that were specific to finance and eliciting generations or responses that would be composable to tabular reasoning. So if the base model just can't perform regardless of the context that you give it, you have to use a more nuanced approach to model training to bring out that capability.
Okay, are you training the model based on fundamental model? If yes, what fundamental model are you using?
The foundational model we used in this presentation was Llama 2, but we've actually in the process of updating the model to Llama 3.
Okay. One question from my side. What interesting challenges you have when you build your infrastructure for training and for inference?
Those are many challenges because it's a hard problem. I think the main thing is how do you balance the memory network with the computational flops of the chips. So basically, any given larger model, once you get past 13 billion parameters, when you're doing the training, you're going to have to do multi-node training. And that means that you have to have a lot of machines communicating with each other. Now, when you have to shard those weights, you have an entire set of distributed training algorithms that you have to apply. And with every model, it's actually different, the strategy to fully optimize probably the communication pattern. So you have to run a lot of empirical investigations with that, and then also build a robust training harness that is fault tolerant and will optimize that the training throughput. As for the inference side of things, it's a balancing act between lossy techniques such as quantization and how far down you want to reduce the precision of the model in sacrificing the model quality, and also uh, caching the available attention mechanism to batch correctly the set of requests that go into your inference server at runtime for all of that. So we developed a lot of that in house, as well as bringing in components from standard infrastructure and frameworks, and we needed to do that because of the fact that everything we face enterprise and we sell to the enterprise. So all those things are necessary for us to have in place for any of our customers to want to use us.
Good. Hallucination, techniques to mitigate hallucination. Can you elaborate the specific strategy used in Albatross?
Yeah, I touched a little bit about that. That really was in the supervised fine tuning step of the presentation. So using supervised fine tuning, we can ground the model to produce the proper generations. So in a lot of uh, in a lot of instances, what happens is the model doesn't know the boundaries of its knowledge, and additionally, you need to give the model particular pairwise examples of responses and questions where it has a little bit of distraction. So, like where it needs to figure out to ignore some context, otherwise it elicits the wrong response, or it will leverage some context to provide the correct response. So it's all of that diversity mixing of that synthetic data that allows you to mitigate the hallucination and also produce more consistency.
Mhm. Yeah, more about hallucination. What are the best techniques to avoid the hallucination using a RAG-based solution to extract medical data from medical documents, but faces the hallucination?
Um, I think there's a lot of papers written on this. It's hard for me to give a one size fits all solution for that, but in particular, I would focus on the retrieval step, and also doing really good evaluations on top of the model you're going to be leveraging on its ability to knowledge probe the boundaries of its capabilities.
Good. Uh, about deployment challenges to deploy LLMs in production, can you share lessons learned from deploying Albatross in real-world financial applications?
Yeah, deployment is always an interesting question because it's the main aspects you have to think about it are cost to latency efficiency and throughput efficiency. So uh, oftentimes what you'll be balancing are actually hardware constraints on the customer side. So we do a lot of virtual private cloud deployments, on-prem deployments, and not everybody has H100s or even the newest NVIDIA B200s, and you have to be able to actually run on consumer cars a lot of times. So that completely changes the distributed inference strategy that you'll probably be using. And also, you have to understand what the data access patterns and the usage patterns of the model will be in somebody's company. So it doesn't really make a lot of sense to throw a lot of consumer cards on a model and shard that model to be able to facilitate usage that really isn't high, and it really doesn't have like burstiness within there. It's all about controlling the burstiness of the latency and throughput of your model requests responses. So in that you have to work with the client and look at the data for like the query patterns, and also understand what the requirements are for downtime for these models.
Mhm. It will be appreciated to elaborate on the use cases unlocked by your LLMs. the cost of continuous training, fine-tuning, and its own its advantage over RAGs. Advantage, sorry.
So I think that for fine tuning, the main advantage of fine tuning comes twofold. One is, in a way, it's prompt compression. So you're compressing the context that the model has seen many, many times before to elicit a specific response. And at the core, when you train a model, it's doing mapping, and it just maps all the relationships and all the tokens and the responses tons of times, trillions of times, to finally have emergent capabilities and reason and connect other concepts together that it otherwise haven't seen. Now, for RAG, you're sending in all of that context during runtime to elicit that response. What does that mean, though? For like, I'll pose out a question for that because I think that's very top of mind for us too. What does that mean for long context models? Like, we recently released a 1 million context length Llama 3 model that we trained further. It's been shown that using the in-context learning abilities of models, if you can get that correct, it actually elicits and maps and proxies for a lot of the capabilities of fine-tuning. It may actually even be more useful than fine-tuning in many cases, which we found. So when you're looking at those things, I think what it requires is a very close set of eyes on what is the expected size of the examples and how hard the task is to learn.
Mhm. How can an LLMs combine quantitative and qualitative data effective to answer a query?
I This is a interesting question, and it's very high level too as well. But I like to think about it. If you're talking about quantitative data, I assume you're meaning tables or numbers, and then if you're talking about qualitative data, it's text. The main issue about of all of that is for quantitative data, if you want the model to do fine grained calculations, that's not really what the model was built for, because neural networks are uh, the universal functional approximators, right? Like, that's what deep learning is all built on top of. So there's a little bit of lossiness with respect to leveraging these models to be calculators. Where instead, what you want to do is you want to use tools for those aspects. If you can actually specifically identify the times that would be useful. So if you even look on OpenAI or ChatGPT 4, the tool usage capabilities are what make it powerful when it needs to do things like generate Python code and debug certain aspects of code, right? It needs to do the verification step like any human would. Now, with the qualitative data, you leverage the model for synthesis in its ability to go over all the tokens in a context and find the concepts and link them together to properly answer your question or properly take action on a task. So I think it's figuring out how to best leverage a model within a system rather than looking at a model as something that you require a question and an immediate answer out of in a zero shot fashion.
Uh, Good. What specific tokenization techniques do you recommend to use for financial data?
I think extending tokenizers is interesting. There's definitely research out there that uses. There's actually two approaches. One is you can effectively assume tokenizer free, so you should use byte. You basically use bytes as your tokens rather than creating a specific vocabulary. Now, if you want to extend the vocabulary of a model, that becomes a little bit nuanced because for finance, if you do want to apply that, you're going to have to train the model further and ensure that the tokenization pattern hasn't destroyed some of the capabilities of the model that were in the pre-training. In particular, I think what I look at for that is I tend to not want to add too many special tokens to the data, particularly since the vocabularies of these models are so large now. So, for instance, the Llama 3 model vocabulary is much larger than the first one. That's because with a larger vocabulary, you give the model a little bit more freedom in the parameter space to learn a concept. So, um, I personally wouldn't go about adding special tokens too early on when you're training these models.
Yeah. Did you have to change the vocab size for the tokenizer and or add any extra special tokens to the data?
Not for Albatross. We didn't go about that process.
Okay. Would you like to work with you? Are you hiring in AI role?
uh, Currently, we are in process of expanding our team, but yeah, I encourage folks to always look at our website. These roles come in and out fairly quickly, and as a fast-growing startup, it'll always be, an iterative process at which we evaluate our team needs.
Uh, Good. I think on this question we will finish our discussion because I know that you need to have hard stop. And thank you that you come to us. And I hope you will join also to our Discord and we continue this discussion and answer for all other questions which we still have. Thank you, Mark, that you was with us and share your expertise. And thank you for all who was also with us and listened this webinar.
Yeah, thank you very much. Appreciate you having me on, and I hope everybody enjoyed the experience and thought it was informative.
Yeah. Thank you.
Cool.
See you all on the next webinars.
Thank you. See y'all.